curve is the same thing as dd epsilon dt of the curve. So that that's just like something that you know from your calculus course. So now we use that we know this dd epsilon we can replace by the covariant derivative plus something normal. So you can write this using the Gauss-Weingarten map as this expression plus second fundamental form evaluated at dd epsilon of the curve times ddt of the curve and then the normal direction. And similarly here, by just using the Weingarten formula, but now for ddt, we can write this one as covariant derivative of ddt of dc of the epsilon plus the second fundamental form evaluated at dc of respect to t and dc with respect to epsilon. And then again, there's a normal vector. And now the nice part is that the second fundamental form was symmetric, that we had like shown at some point. So we can change the arguments and we get the same result. So you see now that this term here and this one term here, they just cancel. So normal contribution cancel since second fundamental form is symmetric. And what you end up with is exactly this formula that I claimed here, is that, the covariant derivative of the partial differential commute. Good. So that finishes the proof. One small remark in that direction. These properties that we are just shown properties axiomatically characterize the covariant derivative. So if you say like I could have defined the covariant derivative as the unique operation that has these kind of properties. So it's like in some way these properties uniquely characterize the covariant derivative. Okay, so that's nice, but actually not what we were, like these covariant derivatives and stuff, that was not what we were setting out to actually show and discuss. What we wanted to, from the beginning, was actually discuss what is like meaning for a curve to be or two vectors to be a parallel. So let's return to that question. So let's see be a curve, like say, or maybe directly write the field. or the Gauss Weingarten formula applied to x, which is just the tangent vector field, implies that the second derivative of x, which is just the acceleration, so this is ddt of c dot of t. Now we apply the Weingarten formula. We can write that as ddt of the curve plus the second fundamental form of c of t in the direction the normal c of t. So now we here assume that, like, for example, that if c is that's a unit speed curve, then this guy here is just a normal curvature. Curvature of the surface. It's not a normal curvature of the curve, it's a normal curvature of the surface in the direction c dot of t. So from this we can derive the following nice formula of a theorem that in some way combines all these observations, namely let C be a unit speed curve and E1, E2 and E3 be a frame adapted to S with the property that E1 is proportional to C dot, which because it's a unit speed means that they have to be actually the same. Then we have the following properties, namely that the covariant derivative of C dot of t equals to the Gaussian curvature times E2 of C of t, and also the normal curvature of the curve equals to the normal curvature of the surface in the direction of C of t. So that's this observation over there. So in particular, C, the curve, is a geodesic if and only if the k of t is 0, but k of t is 0 if and only if the covariant derivative of c dot is 0. Okay. Okay, so that's like the upshot that we now gained, and essentially it's like combining these two formulas that we had before. Like the first one was expanding the second derivative to c dot of t instead of in terms of k of t and n of t. So it's essentially what we had before is that k of t, 2 of t plus kn of t e3 c of t. And then the theorem just follows by comparing these sides. So like you really immediately see that the t of c of t has to be the first term, and the normal term, the kn of t, has to be this expression, which is just the normal curvature of the S. So it's, you get immediately the result. So it's really essentially just this formula that we had before, combined with the Weingarten formula applied to this guy. So this is the important step there. Okay. But we wanted to actually, like we didn't start it with like making sense of covariant derivatives. What I tried to tell you at the beginning was like, what is this connection that we have from geodesics to something that is parallel? And now all that we did was essentially reformulating one of these equations in terms of this covariant derivative. So we still have to talk a little bit about why that would be something that is related to parallel. And the idea here is essentially encapsulated in the following theorem. Which says that given a curve C in S and a vector which is x0 at the starting point of the curve, and it's tangent to S, then there exists a unique vector field x along C satisfying the following properties: that it has ddt of x of t being given by this equation, that it has to be 0, and that x at the 0 point is the given vector that we started with. So the setting is essentially this. We have our curve C. We are given one vector which is x0, and then this theorem tells us that there exists an x of t. So if for every point we get a vector which changes, so that's x of t, in a way that this covariant derivative is 0, and x of t, this vector field, is called parallel transport of x0 along C. So perhaps, so if I'm drawing it in the plane, then the better picture would actually be just taking the parallel transport of that. Namely, I take that vector and I move it like parallel. So what I get is like so I move that vector and I just like parallel translate it along my curve. The theorem says that that there exists only one vector field that is doing that job. Like if I change like this vector here, then all vectors that are like given here, they change like follow suit, and they are uniquely defined once I give that vector. Okay, let's have a look at a proof. Suppose that ddt, so suppose we have one of these vector fields such that it's 0, then also by the properties that we had discussed, if you first take the norm of x and take the derivative with respect to t, what we get is that we can plug in the ddt in the first slot of x plus the second slot but this term here is 0 by assumption, and this term here is 0 by assumption, meaning that the norm of x has to be constant. Say like some constant. So every vector field that satisfies this property has to be a constant vector field. So hence, if you like choose a frame, if E1 and E2 is a tangent frame, then we may assume that it's defined on the whole curve, or as we do it like on smaller patches of the curve. Then we can write x of t as two functions in E1 and E2 direction, but we know that these functions have like both length r, so we can write it in particular as r times cosine phi of t E1 c of t plus r of sine of phi of t E2 of c of t. And so the problem is now reduced to find this angle function. Angle function phi. So just by the property that it has constant length, we know that there is essentially one function that tells us by how much do we have to rotate x of t with respect to E1 and E2. So like, especially if E1 is like, it's like just like you'd have E1 and E2, they are given, and then like you know that your given vector x of t has to be some kind of rotation in respect to E1 and E2 because they form like an orthonormal frame. Okay, so we need a formula for the phi, and we get that formula by taking the covariant derivative of x and see what happens. So we know that zero, or that the covariant derivative of x that we want to be 0. So let's calculate the covariant derivative of that guy. And what we get, so we just take the formula that we had for the definition of the covariant derivative. So that's really back to the definition of dt of x. Whereas, like, decompose x in something in E1 and E2 and then take the derivatives. So what we get here is that we have minus r times phi dot sine of phi plus r sine of phi omega to 1 c dot of t in E1 direction plus phi dot cosine phi plus cosine phi omega 1, 2 in the c dot direction. And that's our E2 part. But that's nice because this expression over here equals to just minus omega 1, 2. So if you now compare these sides, then we have that they are essentially the same thing, with here minus sine of phi being outside, and here we have plus cosine phi. And otherwise they are like exactly the same kind of formula. So we get that this one is 0. So we get that this one is 0 if and only if and that's a pretty important formula. We have phi dot equals phi dot plus omega 1, 2 of c dot of t equals to 0. So that's a formula that tells us the phi in terms of the omega 1, 2. Okay. So the last step is to, we can just integrate that formula. Because this side here, this omega 1, 2 term is just like a function of t. So we can just integrate it. And phi of t equals to phi of 0 minus the integral of to 0 of this function omega 1, 2 c dot of tau d tau. So that shows you that phi of t is uniquely defined once you know phi of 0 by this formula, and phi of 0 is uniquely determined by x0 because it's the angle, by definition it's the angle. If you look back to the formula, it's the angle of rotating x0 with respect to E1 and E2. So it's the angle that you have to rotate at the beginning, but it's kind of your starting angle. So that shows you in summary that this phi of 0 is uniquely determined by x0. Then from this formula you get that phi of t is uniquely determined. And once you have your phi of t, you plug it in this formula to get that x of t. So everything combined means that x of t is uniquely determined once you know x0. So, in summary, x of t is uniquely determined by x0. So that's the proof. So a few remarks that are important about this is the angle function theta is determined by this equation that we had up there, that phi of t plus omega 1, 2 of c of t equals to 0. And you can think of that as a new interpretation of this omega 1, 2. So you can think of that as maybe as a like the other way around, where you maybe say like phi of t is given, then it has to be omega 1, 2 of c of t. So that gives you a new interpretation of omega 1, 2. So omega 1, 2 at least in the direction of the curve is the rate of the rotation that is needed to stay parallel along C. So the point here is that like this equation doesn't depend on any x or something. So like you can think of that as once you give your omega 1, 2, you can find like a phi by this formula if you have a curve. And then that angle gives you a rate of change that you have to turn around like E1 and E2 such that you get a vector that is parallel. So that's the interpretation here as some kind of rotation. So this omega 1, 2 is some kind of like a change of rotation that is needed in order to stay parallel. Some more remarks. First of all, for the plane, we have omega 1, 2 just being 0. There's no intrinsic curvature of the plane. So phi is just a constant function. And in particular, like phi doesn't depend at all on c. And does not depend on c. Like in general, this formula, of course, depends on c, right? Because it's like here c dot. But here and there, for the plane, the second part just vanishes, and then phi is just like the constant and doesn't depend on c. So that means that the parallel transport does not depend on the curve chosen to connect two points. So the picture is I give you 2 points, and you give me a curve, and then we do parallel transport along that curve of a given vector. So we have, say, a point P and Q, and we're given a vector x0. And then you give me a curve. Let's say we choose like this curve, and then we do parallel transport along that curve, which in the plane is like just very simple. We get like this kind of curve. But you can also give me a completely different curve, say this kind of curve, and then I would need to do a parallel transport along that curve. So I start here, I do parallel transport along that curve. And what happens is that the endpoints, like at the endpoints, the vector that we get are the same. But that's special for the plane. Like this behavior that it doesn't depend on which points I take, like the parallel transport. It's like so intuitive, right? Like you do that in class and like in kindergarten when you have like your teachers telling you first do parallel transport. You take like your lineal and you move it on your piece of paper. It doesn't depend on which way you choose like your curve to where you take the parallel transport along. But like on surfaces, it's actually no longer true that you get the same end vector. So that's the remark here, but on surfaces, phi depends on C dot, or like, let's say on C. So the parallel transport of a vector from P to Q depends on the curve chosen to connect. In particular, if you have two curves, so if you have like a closed curve, you just walk once around, that also means that you might not get the same vector back. So say 1, 2 to S is a closed loop in S, then the vectors x of 0 and x of 1 are rotated by an angle which is usually denoted as the holonomy of C, which is, by this formula, it's just the integral up there. It's like phi of 1. So it's phi of 1 minus phi of 0. And using this formula, we see that it's the same thing as minus the integral of 0 of 1 of omega 1, 2 psi dot tau d tau. But now you go back in your head and like think, okay, like we have seen things like that. That's the one form. In the one form, we plug in a tangent vector and then we integrate what we get. So this one is nothing else than minus the integral along the curve of the connection form. And it is called the holonomy angle. So if you go once around the loop, you might end up with a different vector. So that's the plane picture. But on the surface, we might have like this view that we start at like C of 0 here with some vector x0. Then we do a parallel transport, which now might rotate that vector a little bit for some, as we go around. And then as we go back, this vector, which is the x1, our end vector here, might be really rotated by a vector, by an angle here, and that's the holonomy, the so-called holonomy angle. And as a small homework, I let you think about it, and next time is if you have this sphere and you take just like the curve that is given by just like having at a given height you walk around the sphere, and then you have some angle, some vector which is just pointing like to the north pole here, and you do parallel transport around that vector. What would be the angle? So what is the holonomy of that curve which is just walking around the Earth at like a given height? So that we discuss that next time. So still enjoy your evening, and then see you next week. Oh, by the way, someone asked me about the exam. I still don't know exactly when the exam will be. So, what? Like, like someone asked me if I already know when the exam will be. I asked, but like no one knows yet exactly the date for the exam. So I will let you know about the date of the exam once I know it. So, like I don't know when the exam will be. So, yeah, thanks. What? Yes, that's very much related to Berry phase, yes. Yes.